Hello everyone and welcome to the first video of the second lecture of the course on metric spaces. In the last lecture we defined what's a metric on the plane, we defined more than one metric, and we learned what it means to measure a distance. Now, however, I want to ask you another question. We want to measure distances in real life as well, which means that if you're, for example, here and you want to get to this other point here, and in the middle you've got a mountain, then the metric we introduced in the plane in the first lecture would measure for us the distance from the point here to the point here going through the mountain, which means as the crow flies. However, we cannot go through the mountain. We need to go around it in this way. Therefore, the distance in which we're really interested in if we want to move from the first point to the second point is not this one, but it's the distance going via this other path, which means that we have to give a definition of the length of this path or curve here. Now, in the example of the metric on the plane we defined in the first lecture, where the distance between 2 points P and Q with coordinates xp, yp, xq, yq is given by the square root of xp minus xq squared plus yp minus yq squared, then we said that this number here is exactly the length of the segment connecting P and Q. However, this is not true in general for every metric, which means that, for example, if we stick to the plane and we draw the y and the x-axis, then we might define a distance such that if we take the point P and the point Q, then the distance between P and Q is not necessarily equal to the length of the segment connecting P and Q. This means that we have to give a definition of the length of a segment or of a curve, as we had before, which is based on our definition of the distance. So let's try to give the definition of the length of a curve, or at least understanding which might be the correct definition. In the plane with the distance we introduced, we already know that the length of a segment is given exactly by the distance between the endpoints. So let's try to work out what's the correct definition in the plane with this distance of the length of curves, and then we will generalize it to other metrics as well. So we draw a curve starting with a point P and ending with a point Q. We want to measure the length of this curve, and we already know that the length of a segment is given by the distance between the endpoints. So let's say that we pick a lot of points on this curve and I'll call them P1, P2, P3, and so on, and we pick as many as we want, with the only restriction that they must be on the curve. Let's call the last one Pn. Now, what we know is how to compute the distance between P and P1, which is exactly the length of the segment connecting P and P1. At the same way, we know how to measure the distance between P1 and P2, which is the length of the segment connecting them, and so on and so forth. Notice, however, that the segments for the first points seem to lie on the curve, but it's clear that, for example, if we take this point here and this point here, then the length of the segment connecting them is the length of this segment, which is completely outside of the curve. So we have to be careful, because even if it seems that the segments are very, very near to the curve, depending on how we choose the points, this segment might be very far from the curve, completely outside the curve. However, taking these points on the curve, one thing we might say is that the length of the curve is approximated by the following sum, which is the sum the distance between P and P1 plus the distance between P1 and P2 plus till the distance between Pn minus 1 and Pn plus the distance between Pn and Q. And it is a first approximation of the length of this curve connecting P and Q. We claim that this is a nice approximation, but we have to prove some properties of this approximation. For example, we would like that this number, which is the sum of these distances, becomes nearer and nearer to a fixed number, which should be the length of this curve connecting P and Q. To understand why this number approximates a fixed number, consider the subset of points we have already chosen on the curve, and let's say we add another point here that we will call P prime. Then I claim that the sum we've written down here, where we don't have P prime, is smaller or equal than the sum where we also add P prime. So it's smaller or equal than the distance between P and P1 plus till the distance between P3 and P prime plus the distance between P prime and P4 plus till the distance between Pn and Q. And how do we prove this claim? Well, it is a consequence of the triangle inequality. Indeed, all the terms here are the same, except for the one concerning P3, P4, and P prime. This means that we have to focus only on the part of the curve which is very near to P3, P prime, and P4. So let's draw this part of the curve. Here's P3, here's P4, and here's P prime. Then, if we draw these three segments connecting these 3 points, we see that is exactly the triangle inequality that tells us that the distance between P3 and P4 is smaller or equal than the distance between P3 and P prime plus the distance between P prime and P4, thus proving the inequality we claimed before. But the question is, why does this inequality here tells us that we're giving the correct definition? Of course, it doesn't prove it, but it gives us a hint that it's probably the correct way to proceed. Why? Well, because we would assume that the length of such a curve is finite, because we can draw this finite curve. But then, if this is true, as we have a number, which is given by this sum, that grows and grows and grows, but it's limited by a fixed number, then this means that the sum will approximate and at some point will stabilize. We will see some examples of this thing, and the number to which this sum stabilizes will be exactly the length of the curve we are interested in. However, as this is only an hint, we should see some examples in which we actually can compute the length of the curve and prove that is exactly the length we would expect it to have. For example, the first thing we could do is to try and measure the length of a segment whose endpoints are P and Q and see that the length computed using these sums is exactly equal to the distance between the endpoints, thus recovering what we already know, that the distance between P and Q is exactly equal to the length of the segment connecting them. So let's try to apply this definition to the computation of the length of a segment. Let's draw the axes, y and x, and let's take 2 points, P and Q, of coordinates xp, yp, xq, yq. And let us draw the segment connecting these 2 points. We want to compute the length of this segment using the formula we just defined. So we have to take a point, or more than one, on this line. Let's say we take a point here, P prime, and we want to compute the sum of the distance between P and P prime plus the distance between P prime and Q. However, this computation is just telling us that we have to measure the length of the segment from P to P prime, by definition of distance, plus the length of the segment from P prime to Q. And this will necessarily be equal to the length of the segment from P to Q, simply because the segment from P to P prime followed by the segment from P prime to Q is exactly equal to the segment from P to Q. However, we can explicitly write down the formula and see that this distance equal to the distance from P to Q. However, instead of using square roots and computing the quantities explicitly, let us use Pythagorean theorem to prove the equality between these 2 quantities. First of all, let me draw the rectangle triangle whose hypotenuse is the segment connecting P and P prime, and the rectangle triangle whose hypotenuse is the segment connecting P prime and Q. Notice that the segment connecting P and Q is the hypotenuse of another rectangle triangle, which is the last one I've just drawn. The distance between P and P prime is the length of the hypotenuse here, and the distance between P prime and Q is the length of the hypotenuse here, while the distance between P and Q is the length of the hypotenuse here. However, the length of this side of the triangle is exactly the sum of the length of this side and of this side. And in the same way, the length of this side is the sum of this length and of this length, which means that the sum of the length of the segment connecting P and P prime, which is the hypotenuse of this rectangle triangle, and the sum of of the segment connecting P prime and Q, which is the length of the hypotenuse of this rectangle triangle, must be equal to the length of the hypotenuse of this big rectangle triangle, which is exactly the length of the segment connecting P and Q. This reasoning can be applied to any number of points we choose on the segment connecting P and Q, which means that the sum we've written down here for every subset of points will always equal to the distance between P and Q. And in turn, this means that the definition we gave fits with the definition of distance we gave in the plane. Indeed, this will be the definition we will use to compute length of curves during the course. In the following lecture, we will see some other examples of length of segments in different metrics on the plane. See you in the next video.